Let's look at a work example of using secant lines and an informal limit to figure out what we think the slope of the tangent line to a curve is going to be. So we are looking at the graph of the natural log function, y equals log x or ln x, and we're looking at the point 2 comma log 2. So we're looking at where x equals 2, y is therefore of course log 2, which is about 0.693. And we'd like to get an idea of what the slope of the tangent line is going to be. And the way we're going to do that, and the official definition, is we're going to sneak up on it. And the official way to think about that is called a limit. And we're going to look at the slopes of all these possible secant lines where we start from P and go to some other point Q, which can be either to the left or the right. I'll do a bunch of ones to the left and maybe just one to the right. And what you notice, and this is what people typically see when they investigate this, is that when Q is near P, it really doesn't change very much. And it looks a whole lot like a line that is just going exactly in the same direction as the curve and is just barely touching it at that point. And we're going to call that the slope, call that the tangent line. And the slope of that tangent line is basically our definition for the slope of this curve at the point P. So how do we look at that? There's going to be more formal ways to really convince somebody of this calculation, but it's very, very useful and connects very well to practical applications to just look at some values. So I'll look at that pretty quickly. So let's say, suppose we start out with Q actually pretty far away. Even though we're really interested in Q nearby, we get a better picture here if we start out fairly far away and then we see how it changes. And the numbers also are simple if we start with Q equals 1. There, the y value at Q is just going to be 0. Log of 0 is always going to be 1. And so we're going to take the slope of that line, so we're just taking the difference in the heights, yp minus yq, divided by this difference in the x values. Here that's just 1, and so we get the 0.69315. Okay, so that's just what it is. Let's go closer. If I peg this at about 1.8, I'm going to go ahead and use Geometry Sketchpad here to give me a rough answer, and then I'm going to show you that I pre-calculated stuff. Actually, that's pretty close, 1.8. Now the y value is 0.5873. It's much closer to 0.693. And the slope, I went ahead and had it calculate exactly the ratio of yp minus yq over xp minus xq. Let me show you that calculation just one more time with all these numbers that are a little more complicated. We've got 0.69315 minus, and let's get an exact value as possible for the log of 1.8. This can do that for me. Okay, and I probably want to get pretty good accuracy here because the whole point is that when you get close, let's say that's pretty good for right now. When you get close, you're going to take the difference of two very, very close numbers, and you want to get that very, very precise. And then on the bottom, of course, it's not too bad. That's just going to be 0.2. Oh, and so let's just get the numerator here, just the difference in the heights. I want to write that down on my table. Okay, so this was 0.587786. Let's put that in math mode just to make it look consistent. And then so when it goes over 0.2 from Q to P, this is going up 0.105364. Okay, so it's kind of suggestive. That's interesting. What is the actual ratio there? Let me get that out of the way. Okay, about a half. So I think if I had never seen this example before, I would expect you've got this funky weird number. We might have seen it before, might be familiar with it from dealing with logs and 2's and stuff before. And then there's this funky number. Obviously, it has something to do with natural logs and E and all this crazy stuff. I would kind of expect these numbers to be weird and unpredictable and not necessarily pretty. And the really interesting thing is that when you get really, really close here, reveal the pre-calculated stuff. Let me just delete this. What we discover is that in fact these numbers are getting really, really close to 1/2. So here's something where I made Q really, really close. I don't think with Sketchpad I can quite quite replicate that, but I'm going to take it really, really close. At least get to 9.8. Okay, that's pretty close to this 9.8 here. And we're seeing that 5026. It's very, very close to this. And I could get a little bit closer. Actually, I can get pretty close, though. That's pretty good. Okay. And what we notice is this slope is getting really, really close to a very simple number. Now, there's absolutely not a proof that this is really, really, the trend here is towards exactly 1/2, but it's suggestive. If we take Q a little bit further, we always want to try and come at it from both sides. So I'm going to take Q fairly far away. Okay, it's something a little under 1/2. And then as I take Q closer and closer, notice it really is getting very, very close to a surprisingly simple number, very, very close to 1/2. And here I did a more explicit calculation, more careful calculation. 2.0002 gives you something that's super close to 1/2. So our guess might be here that the slope of the tangent line is perhaps 1/2. That's maybe too optimistic, maybe too bold. Turns out, though, that it's absolutely true. And that's pretty cool. We've seen, I usually have in my classes, have people do a lot of experimentation. And one thing we typically see is that tangent line slopes are no more complicated than we'd expect, and sometimes a bit simpler than what we'd expect. I feel like this is a good example where it's way simpler than we might expect. That these weird numbers that we have to memorize, 0.6931, all this kind of stuff, goes away, and that somehow the slopes of this natural log graph are simpler than the heights of the graph. And we'll discover that's absolutely true and pretty deep.